Okay.
So we're very happy to have Jeremias Damia today. Jeremias graduated from Universidad Nacional de La Plata, supervised by Diego Correa, and he's now a postdoc at Centro Atomico Bariloche. And tomorrow, this year, I guess, Jeremias will be going to Brussels. Today,
hopefully.
He will talk about, sorry? Say it again?
Hopefully.
Hopefully. Yes, we all hope for everybody. So today, Jeremias will talk about non-Fermi liquid, quantum critical points, and the IR divergences. Please.
Okay. Well, thank you, Paolo and Luca, for this nice opportunity. In this occasion, I would like to talk to you about work we've done with Gonzalo Torroba and Mario Solis. It's been released 2 weeks ago, and it's about a particular example of a quantum critical point and a quantum critical region associated to it with displaced non-Fermi liquid behavior. So let's start with some definitions and a piece of motivation afterwards. So a critical point essentially occurs at the transition between two phases of matter at 0 temperature. And it generically occurs when some relevant coupling takes a particular value, a critical value, let's say. And these couplings are usually tuned by varying certain external parameters, let's say magnetic fields, which is pretty common, or doping, etc. A simple model of this, which maybe you all are familiarized with, is, for example, the quantum Ising model with the transfer magnetic field. In that case, this transfer magnetic field, or the intensity of this field, interpolates between a paramagnetic phase at very large fields and a ferromagnetic phase with longer rank shorter in the opposite regime. And in the middle, there's a certain value of this magnetic field at which the quantum critical point is. So this is a simple example of that. Of course, the theory at the critical point is a scale invariant, and it has a certain characteristic scaling behavior, which is essentially what we are interested in. And most importantly, once we turn on the temperature on the system, one would expect that for temperatures low enough, the quantum fluctuations associated with the critical point to dominate over the thermal ones. So the scaling behavior observed in this whole region at finite t will be dictated by the critical point. And this is what people call the quantum critical region. So pushing a bit forward is, we are interested in particular in metallic systems. So a crucial feature of our model will be the presence of fermions. And a finite density, of course, the ground state is characterized by a Fermi surface. And as it is well understood from long ago, the solid presence of this Fermi surface allow generically to determine most of the universal properties of these simple models. And this is the principle behind the usual Fermi liquid theory. But now let's suppose that we want to go beyond that paradigm. So we need to consider something else. And this is where the critical point essentially gives us what we need, which is Gapless Bosons. And why is that? Well, essentially because the order parameter associated with the transition near the critical point can fluctuate at arbitrarily long wavelengths or arbitrarily low energies. So it's usually well modeled by a Gapless boson. And now if we consider interactions between this order parameter and the Fermi surface, one would expect that in some situations, these interactions had strong effects at arbitrarily low energies, thus breaking the Fermi liquid paradigm. And this is, if this is the case, we say that the quantum critical point displays non-Fermi liquid scaling or behavior. So this is generically materialized by anomalous scaling of fermionic excitations. And throughout all this talk, when I say anomalous, I mean not accounted by the usual Fermi liquid theory. So in the presence of such a quantum critical point, one would expect to be a quantum critical region, as I mentioned you in the previous slide. Now, displaying some non-Fermi liquid behavior, for example, in transport properties associated with these fermionic excitations, for example, in the resistivity. And that's why these models are so appealing, because they stand as a plausible explanation for the anomalous scaling of in strange metallic states. So this is essentially one of the main motivations. And to finish this introduction, I just like to show you a picture of the general phenomenology observed in the cuprate high TC superconductors. So here we are plotting, if you want. Oh, sorry, by the way, can you see my mouse moving here? Okay.
Yes.
Okay, great. So besides most of the complications of this phase diagram, I would like you to focus on the region of optimal doping on the right. Here we see this wedge-like region, which is double strange metal because of this anomalous scaling of, for example, in resistivity with the temperature. And it is very plausible, at least it's conjecture, that this strange metallic phase is generated by the presence of a quantum critical point at zero temperature. So that's a piece of motivation. Another piece of motivation, additional in the case of this kind of compounds, is that usually we cannot go all the way down to zero temperature because there is a superconducting phase taking over at some finite temperature, a critical temperature TC. But in these compounds, generically, this TC it's relatively high. So it is hard to fit in the usual BCS models. And it is also believed that the presence of a quantum critical point might be inherently related with the onset of superconductivity at such high temperatures. So this is another motivation to study these models. And even though if you are not interested in superconductivity, let me just say that generically, by applying magnetic fields, it is possible to shrink the superconducting dome and uncovering then more and more of the quantum critical region associated with the strange metal. So what I like to stress is that this critical region is usually pretty amenable to be tested experimentally. And that's essentially the main motivation for this. So hopefully I convince you that it is interesting to study these models. And let me just line up the task we will be pursuing in this talk. So of course, our main objective will be to characterize a quantum critical region associated with a non-Fermi liquid quantum critical point at zero temperature. In the way, we will have to deal with certain infrared divergences associated with the presence of these soft modes at finite T. And we will see that resolving these divergences will have an enormous impact in our characterization of the critical region. And finally, I'd like just to mention some phenomenological consequences. So let's go to it. By the way, this is a good point for questions if you have one before going to the details of the model. Okay, so let me just describe the model at zero temperature, which is essentially the quantum critical point. The first remark is that we will work in two spatial dimensions. We'll consider a spherical Fermi surface of radius kf, the Fermi momentum, which is usually the largest scale in all these models. And okay, well, in two spatial dimensions, this Fermi surface is just a circle, as here in the figure. We have all the field states inside, and for a given excitation above this ground state, the momentum is parameterized by the angular position on the Fermi surface, this normal vector n, and the orthogonal separation to the Fermi surface, this p pair here. And in a very good approximation, near the Fermi surface, the energy of such excitation can be just parameterized by this linear dependence on the orthogonal separation. So our three-level kinetic term for the fermions will be this one here. Now we will add Gapless Bosons. So they will interact through a usual Shukawa interaction with the fermions. And now an important question arises here, and it's about what is the actual dispersion relation for these bosons at low energies. We could consider a relativistic dispersion relation and ask if this is robust, for example, if this is the correct one for this kind of models. And the answer is that it is not, generically. And this is essentially because there is a whole bunch of mechanisms by which a new dispersion relation could develop. And here, as a motivation, I would like just to show you one of those cases in which there is a different dispersion relation, which is dominated by what people call Landau damping. So this is a fermionic loop. So this is a correction to a bosonic propagator. And at finite density, it has this form, which has two consequences. On the first hand, high frequency modes become gapped, and low frequency modes become overdamped. And moreover, this damping term is usually more relevant than the omega squared term. So generically, one has to neglect the omega squared term in terms of this. So the moral of this is that generically the dispersion relation will be different from the relativistic one. So we will consider, in this case, overdamped bosons right from the outset. And this is generically fine from the effective field theory point of view. In that language, we are not actually asking about the detailed UV completion of this theory. We are just considering there is one, assuming there is one, and at certain scale, which we assume it is large enough, Landau damping on sets. And we are asking about the physics below that scale, all the way down to low energies. So that's the philosophy. We are not caring about the actual origin of the damping term. And that scale is the so-called Debye mass, which I call, it's denoted by MD. And so putting all together, this will be our three-level bosonic kinetic term in our model. And the Debye mass, in the same language of the effective field theory, will act as a natural cutoff in our theory. More important, yeah, sure.
So we should think of this non-local term as coming from having taken some fermion loops into account?
Well, it might be a possible origin for it.
So you're going to keep the fermions in the theory.
Yeah, but let's say that we are assuming that this damping term is there, but not necessarily caused by the fermions we are considering in this model. Because, you know, in this model, we will have a Larsen expansion, and there will be a correction to Landau damping because the diagram is actually the same, but we'll consider that a subleading correction. So you can assume, for example, that there were another kind of fermions which by loops induced this Landau damping term. So this is the philosophy of effective field theory in general. So we are considering.
Well, usually we just put local terms.
Sorry?
Usually we just put local terms, right, in effective field theory. But I guess you're saying, well, maybe there's, you know, if you start putting 1 over q's, when do you stop?
Well, yeah, that's correct. That's correct. Yeah, if you want, in a more exotic point of view, you can consider that the fermions, which we are considering induce Landau damping, and you tune the Fermi momentum to a scale with n in such a way that you can define this Debye mass, and everything is okay. But I generically don't prefer that point of view because it has a fine tuning. I don't know. Yeah.
Sorry, maybe it was generated under RG. Like you integrated already some of part of the fermions, and it introduced this, and you're going to continue to integrate more.
Exactly. That's the way I like more. So you can imagine that we have integrated another degrees of freedom, and they generated this, and we start from this. Exactly. So, yeah. Very good question. Yeah.
Yeah. Your theory doesn't have the fermion now. Is it correct? Or, I mean that you integrated out the fermion to obtain this this overdamped term. So now the theory is only composed of the this boson, or
no. That's what I mean. So now I'm describing the ingredients. So we are considering the boson overdamped just from the outset, but it is not by the fermions we just introduced. So these overdamped bosons will be interacting with this Fermi surface.
Okay, fine.
Oh, sorry. Is there any background noise?
Yes.
Yeah, because the police is outside, because we are locked down, and the police is in a control. So sorry for that.
It's good. It's not loud.
Okay. Okay. So this is essentially the philosophy of the model, but that's a very good observation. Okay, and let me just talk about the absence of a mass term, and this is a priori not ruled out by the effective field theory, nor by any symmetry imposed to it. So it generically will be a mass term here, but here it comes the tuning. So we are tuning the model to criticality because we want to describe the critical point. So we are assuming that we are close enough to the critical point such that there are no mass for disordered parameter fluctuations. So there is an implicit subtraction by means of any UV local to counter term. Just as a clarification, we will find at finite t that there are other mechanisms by means of IR physics by which such a mass can generate, and it cannot be cancelled this way, and this will be crucial at finite temperatures. But for now, we have gapless bosons with this damping term.
So is the biomass necessary for your results, for your conclusions?
Well, it's your large parameter if you want. It's one of the control parameters.
Can't you use temperature as
Well, usually, yeah, generically there will be some ratios between, temperature and the biomass, or there will be another scale in the game in the following, which is the non-Fermi liquid scale. And you will have to consider ratios between non-Fermi liquid scale and the biomass and the temperature generically as control parameters, yeah. But let's say that the biomass, besides the Fermi energy, which is of course pretty beyond the biomass, it is the largest scale here. Okay, well, what we just been talking about, it's pretty common in this kind of models. As you can see in the literature, generically, bosonic modes associated with disordered parameters displace dispersion relations which go beyond the relativistic one. So, time for some terminology that maybe you already know. The dynamical exponent is defined by the power law scaling behavior between frequency and momentum given by the dispersion relation. And so, for example, the relativistic boson is, of course, has Z equal 1 because by relativistic invariance, you need the frequency to scale the same way with the spatial momentum. But in our case, we'll consider overdamped bosons, which are usually called the Z equal 3 bosons. So in this language, our model is a Fermi surface interacting with the gapless Z equal 3 boson. That's the model. Just one remark, one additional remark about the model in 2 dimensions, spatial dimensions. The Shukawa interaction is relevant as it has positive unities of energy. So the model is naturally strongly coupled. So that leads to our final ingredient, which is to promote the fields to transform in a non-trivial representation of a global flavor SUN and solve the theory in the Larsen expansion. So this is all put together. We have the fermions in the fundamental of SUN. We have the overdamped bosons, which we'll consider in the adjoint. So this is a matrix Larsen. And we have the usual Shukawa coupling with the relevant coupling G, which is kept fixed as n goes to infinity, as usual in a tough expansion. So that's the model, 0 temperature. So, and in particular, this model is perfectly solvable in the Larsen expansion. And the most important thing is what one obtains by solving the Schwinger-Dyson equation for the fermionic self-energy. There are two important things here. The first one, and the most important one, is the non-analytic dependence with the frequency, with a power law which is less than 1. So if one has this, one would expect that at some point, for frequencies low enough, this term will dominate over the linear term. When that happens, is determined by this dynamically generated scale, which we call the non-Fermi liquid scale, lambda. And essentially it says that for frequencies below lambda, the quantum corrections are stronger than the usual linear term. And the fermions display this new dispersion relation, the anomalous dispersion relation, given by the same considerations as for the bosons by a dynamical exponent, which is now 3/2. So when you heard that people say that this kind of interaction destroy quasi-particle coherence or such an statement, is essentially this thing what is happening. Moreover, the Shukawa coupling in this model flows to a finite order 1 value given by a 0 of the beta function. So we have a perfectly self-consistent fixed point with non-Fermi liquid dynamics, and this is the theory of the quantum critical point. So is there any more questions about the zero temperature picture?
Can I ask a question?
Sure.
So what is the blue blob on these propagators? And also, does the boson get updated? I mean, does...
Well, yeah, exactly. Yeah, this figure it's probably a bit misleading because the actual bosonic propagator only has Landau damping. So this blob here will consider subleading effects in 1/n. So we are not considering actually them, but we are solving, if you want, an equation with a wavy line without the blob here, but with the blob here. So we are resumming all the rainbow diagrams.
Okay, thank you.
Yeah, that's a good question.
Momentum dependence on self-energy. Yeah.
Well, actually, you can check that it's irrelevant. Any momentum dependence is irrelevant. So you can scale the momentum down to the Fermi surface, and this is the leading effect. This is usually this also happens usually in Eliashberg theory generically. This is one of the assumptions, but you can check it explicitly. Okay. So let me go further. Just two remarks, important remarks about the quantum critical point. On one hand, we have, as promised, the scale invariance. I just showing here the scale transformation associated to the bosonic variables, but of course there is an analogous transformation for the fermionic ones, but I only need this for the following. The second important remark is that we haven't considering boson self-interactions. And in particular, again, this is not ruled out by the symmetries of the effective field theory. And generically, in 2+1 dimensions, these terms could be relevant in some situations. But it turns out that by this scale transformation, you can check that this term is irrelevant. So the moral of this is that as long as the boson is governed by the Z=3 scaling, a quartic self-interaction is irrelevant. But we will come back to this at finite temperature because it will be crucial to consider this kind of transformations, but they don't affect the quantum critical point.
Question?
Yeah, sure.
Is this fixed point related to Sung-Sek Lee's metallic fixed point, which also has Z = 3/2?
Sorry, what fixed points?
The one obtained by Sung-Sek Lee and collaborators. I mean, I think that their framework is a bit different. I think they basically guess the dynamic.
Yeah. Actually, Sung-Sek Lee, I think I know what you're talking about. Actually, the fixed point studied by Sung-Sek it has some issues associated with this damping term generated by the same fermions which are on the theory. Mm-hmm. So there is some enhancement in the large N expansion, and it breaks at some point. that's one of the main reasons I'm trying not to consider that here.
Right, but is your fixed point different? Are there some?
Well, it is the same in some aspects. So it has a Z=3 boson, and you have a non-Fermi liquid with ZF=3/2, because it's induced naturally by Z=3 boson.
Right.
But on the other hand, here there is no enhancement in the Larsen expansion, because we are considering the damping term as God given, if you want. Yeah, but that's a very important point. Okay. So now we described the quantum critical point. It has non-Fermi liquid behavior at t=0, with the dynamical exponent ZF =3/2, and everything of this, the theory flows to this fixed point for energies below this dynamically generated scale lambda. So now we could ask what happens if we heat up the model. There's a naive intuition here, which is essentially comprised in this figure. So here, the x-axis is the inverse correlation length, or if you want, the characteristic momentum of a given excitation of a typical process. And on the vertical axis, there is the temperature normalized with lambda. So these two lines here are the 3/2 scaling imposed by the dispersion relation. And therefore, inside, between these two lines, in this red shaded region, one would expect that every physical process at this very large correlation, these very large lengths, to be dominated by the quantum critical point. So this is what we call the quantum critical region. And in particular, we could a priori have an intuition of where is the crossover, where this quantum critical region will end. And as lambda is the only scale here, it cannot be in another place but for temperatures of order of lambda. That's the naive intuition about the quantum critical region. So a natural question is if this is actually accurate. And the answer is, of course, it is not. And that might seem a bit counterintuitive, because I say that there are no additional scales. But the answer is that once we turn on the temperature, no matter how small it is, we will see that the model displays a lot of fire divergences, which plug the whole perturbative expansion. And so for having a sensible model at finite t, we will need to find a mechanism to resolve these divergences. And on the way of doing this, a new scale will be generated, and this will change our intuitive picture about the quantum critical region. That's essentially what we will find. And so as these kind of divergences are crucial, let me take a brief detour and take a closer look to them. So what kind of fire divergences are we talking about? Well, in this kind of models, these are naturally associated with the exchange of static bosonic modes. When I mean static, I mean zero frequency modes. At zero temperature, there wasn't any issue with these modes, essentially because as the frequency spectrum is continuous there, the contribution of these static modes was just a zero measure point in the integrals. Everything was integrable and nothing will happen. However, once we turn on t, of course, the frequency integrals are replaced by Matsubara sums, and one had to be more careful with the static mode exchange. To see it explicitly here is the one loop fermionic self-energy induced by the rainbow diagram. So here we have now a Matsubara sum, and this D is the bosonic propagator. So as you can see, the contribution of the static mode will happen when the running frequency equals the external one. So we have a zero here. So we will single out this contribution from the remaining, and we will parameterize the fermionic self-energy by this thermal piece, what we call the thermal self-energy, and the non-Fermi liquid piece, and we call like that because it has the information of the underlying critical point.
A question.
Yeah, sure.
So the first term in the integrand of the self-energy, is that a fermionic Green's function? Why it doesn't have the exponents, the non-trivial exponent? Or the sign of omega m divided by square root. What is this term? This is the Green's function of the fermions?
Sorry. Yeah. There is an implicit integration over the angular variable, which I'm not showing here. Yeah.
Okay.
Sure. But you're right. You will have, and actually this square root comes from there. Yeah. But generically, this will be d2q times the fermionic propagator times the bosonic propagator. Sure, of course. Okay, so we have split this self-energy in these two pieces, and the bosonic propagator is this one here, is the bosonic propagator for the overdamped boson, and of course for omega equals 0, which is what happens here when this frequency equates this, we'll have the 1 over q squared, which leads to a log divergence of the thermal piece. This other piece, as we will see, is perfectly finite, and we can solve the Schwinger-Dyson equation for this. But this is the trouble here. So, of course, that was a one-loop example of how these divergences appear, but they will appear at any order in the perturbation theory, in the perturbative expansion, as long as any higher loop involves a static boson exchange. So we need to resolve them somehow.
Sorry, can I ask you another question? I mean, typically
Sure.
Temperature cuts off the infrared divergence. So it is very surprising that turning on the temperature leads to divergence.
Well, it might.
I mean,
be
you have this infinite beta loop, right? And then the beta circle becomes short, smaller, right? So what is the origin of the divergence?
Well, it's actually it's not a new divergence. It's generically when you have a massless mode in your model and you turn on T, you will find this kind of divergences. So because essentially, if you want, yeah. Okay, maybe maybe I don't have a physically appealing argument. It's just a computational one, if you want. So. As long as you have massless modes, bosons in particular, you will have a propagator which goes like 1 over q squared. And this generically will lead to such a divergence. And unless the other particle in the game fix it some way, but the fermions don't do that job.
This is the usual hard thermal loops that you resum with cactus diagrams and stuff like that in thermal field theory.
Well, there are non-perturbative resolutions for this kind of divergences, but we will see that it doesn't work here.
Okay.
So let me just briefly, to put you in context, just briefly comment about some failed attempts. So the first one is the more obvious one. So maybe the fermions induce a mass at finite temperature. We know that they don't induce a mass at 0 temperature, but maybe at finite T it happens. But of course, as I have said you before, the fermions only contribute to a subleading correction to Landau damping. So they don't do the job, at least perturbatively. So this is the first attempt. The second attempt is a more appealing one. It's a non-perturbative resolution. Essentially, just as we've been talking about, resumming an infinite set of leading order diagrams, there are plenty cases in the literature in which this is the correct mechanism to solve the divergences, because even though at any order in perturbation theory, the diagrams are by itself divergent, the infinite sum of them is finite, usually having some non-analytic dependence on the couplings. And moreover, this is the mechanism that people used some years ago for similar models, but in higher dimensions, and it perfectly worked there. So it is a natural choice here. So long story short, what you essentially do computationally, you regulate the integrals by the usual dimensional regularization, in this case, by the extending the dimension to 2 plus epsilon. You sum all these rainbow diagrams to obtain a Schwinger-Dyson equation for the self-energy. You solve it, and you take of course, you take the limit of epsilon going to 0. As you can see here, this is not the correct answers here, because the self-energy, in this case, I'm just writing the thermal part, it's still divergent. So even it has a lower degree of divergence, because it now goes like 1 over square root epsilon, it is still divergent. And that means that these divergences are too strong in 2 spatial dimensions to be cured this way. But this is a pretty common way to cure this kind of divergences. But it failed here. So that leads us to the third attempt, which is the successful one. And it is essentially by considering a thermal mass, which is generated by boson self-interactions. So you can say that I just told you that we will be neglecting these interactions, and that's true, and that is perfectly fine, as long as the bosons are, the dynamics of the bosons is dictated by the Z=3 scaling. But once at finite t, we have to be more careful, because the static mode, for the static mode, the Landau damping term vanishes. So there is no Z3 scaling for it. So a way to see the effect of the quartic interactions for the static modes, a simple way to see it, is just to consider the effective action for these modes at sufficiently low energies and momentum. So in this case, we have, it is written down here, and we have the kinetic term without Landau damping, of course, and now we are including a quartic interaction. Let's see what happens. Oh, just a comment about this. If we had considered all the frequencies here and the quartic interaction for all the frequencies, the result will be exactly the same as here. So I'm just including this interpretation here for simplicity, but it actually it's pretty accurate. So the first thing that one can check is that by a similar scale transformation, which leaves the kinetic term invariant, now there is an effective coupling which is relevant. So this is the case of it's not exactly what people call dangerously relevant, but fits pretty much in the definition, as there is an interaction which was irrelevant in the UV, but for some weird infrared effects, it became relevant. Other way to see it is that you are in the effective theory for the static mode, you are like compactifying on the thermal circle and just keeping the massless mode. So as the effective theory is now in one less dimension, it's natural for some coupling to become relevant. But besides the interpretation you like most, the important thing here is that we can no longer ignore its effects. And actually, are the effects of these self-interactions the one that generate the mass that cures our problems? And the way to obtain this mass is to self-consistently solve the equation obtained from resumming all these diagrams, which are the Ling order diagrams. Once you resolve the Schwinger-Dyson equation associated to this, you obtain this expression. And an important clarification here is that this mass cannot be cancelled by the tune to criticality of I just mentioned you before. And why is that? Because it is an inherent infrared effect. And that's essentially because any of these diagrams at each order in perturbation theory are IR divergence. But it is the whole resummation, the one which leads to a finite quantity. So it's an IR effect, and now we have to include it. Now the static mode bosonic propagator acquires this self-consistent mass, and we have solved the problem. just a final observation, of course, this mass vanishes in the limit of t going to 0, which is expected because we know that it plays no role in the critical point. So is there any question about how the divergences are resolved?
So can I ask a question?
Yes.
I don't know, in the usual situations that we have, for example, in the phi-4 coupling scalar case, if you integrate out one loop result, maybe I guess you obtain the thermal mass. And what is the difference with the usual situations? You resolve this diagram, and why we cannot use the one loop approximation here?
Oh, sorry, I think I haven't understood the question.
My question is, can we use why we cannot use a one loop approximation at this point if you add the phi-4 interactions? I guess usually in the usual application of the thermal field theory, we still obtain the thermal mass at the one loop level. Is it correct? Or why
you say that there is a mass already at one loop?
Yes.
Well,
I guess
that's not exactly. It might seem it is the case, but it is not actually, because at one loop you are not including the mass in the propagator, so the integral is actually ill-defined. So it is by including the mass that as here in the right. Look that here in the right, this propagator is, as we were considering this, only this diagram, but it is not. It's actually the resummation of all, because we are self-consistently including the result in the integral. That's why we say that we solve it self-consistently. Yeah.
Okay, I see.
Exactly. But that's actually a very important point, because as I have said, any of these diagrams is actually divergent. So it is a very strong IR effect, the generation of this mass. Right. So now we learned that by including the thermal mass, we can render all the integrals finite, and we can go to our original task, which is to solve the model. Before going to that, let me just recall you the splitting of the self-energy in these two components. On the first hand, we have the thermal component, which is the new feature at finite t. It amounts for the contribution of the static modes, as we have seen, which got resolved by the inclusion of the thermal mass, of course. And as we will see, they introduce a new scale, which essentially determines the regime at which this component wins over this. So there will be a scale which determines at which point this contribution will be dominant. And this is the new scale that will break our naive intuition of the quantum critical region. There's the other piece, which is what we call the quantum, if you want, non-Fermi liquid component, and it's just more familiar for us because it keeps the information of the quantum critical point. It will preserve the same scaling dictated by the quantum critical point, and of course it will limit continuously to the critical point self-energy. And we will see it now. So let's start with this, the quantum part, which is more straightforward. The solution turns out to be this, and the most important thing here is that, of course, here we have lambda again, and as I promised, it at t equals 0, it reproduces the quantum critical point self-energy, as it should. And moreover, the most important thing is that it preserves the scaling dictated by the critical point, now with the temperature, with these 2/3 here. So that's the quantum self-energy, what we call the quantum self-energy. The thermal self-energy, it's a bit more trickier to solve, but one can do it numerically. But most importantly, it can be accurately approximated by these three expressions. So in particular, the second and the third contributions are generically decay very quick with the frequency, so they are subdominant everywhere. But it is this regime, the one which will become important. So note that for small enough frequencies, the thermal piece is frequency independent. Again, with the non-analytic dependence on the coupling, as usual in these non-perturbative resolutions, and with, more importantly, with the different scaling behavior with respect to the temperature. And also very importantly, this happens for frequency below a new scale. This is the new dynamically generated scale. Of course, this scale depends on the temperature and it goes to 0 at the critical point. As we know, it plays no role there. But at finite temperature, this scale exists and it determines a region in which the fermionic excitations might acquire a scaling behavior which violates the quantum critical point scaling. So we will see how this materializes in our model. But this is, by now, this is the solution. So let me emphasize here again, this because this is the main point. So we found a new scale. So there we will expect to have a new crossover in our picture of the quantum critical region. And that, of course, will break our naive intuition of the quantum critical region. And in above this crossover, there will be a new scaling behavior, which is still non-Fermi liquid because it is not the linear scaling behavior of the Landau's Fermi liquid theory, but it is more, we call the thermal non-Fermi liquid because it's not now associated with the critical point at equals 0. So to see it precisely, let me establish this hierarchy of our scales, which is pretty natural. We have the non-Fermi liquid scale. We are assuming that it is much lower than the Shukawa coupling scale, which was the former relevant interaction. And of course, everything is much lower than our UV cutoff, the mass divide. So in that case, you will find 3 well-defined regimes as the increase. The one is the critical point, of course, at equals 0. And there is not much to say, just what we call the quantum critical non-Fermi liquid for frequencies below this lambda. And of course, the Fermi liquid scaling for higher frequency modes. More interesting is the second regime, which is valid in this range of temperatures. So the first observation is that this the upper bound is not lambda, but it's a scale which is lower than lambda by means of this hierarchy. So this is a number which is lower than 1. So in this region, we have the 3 scaling behaviors, essentially. For frequencies below the new scale lambda t, we will have that the thermal piece here dominates. And we will have this scaling behavior, what we call the thermal non-Fermi liquid. In this intermediate range between lambda t and lambda, we will have the quantum critical scaling behavior. And of course, the linear behavior for high enough frequencies. So the main point here is that as t it's inside this interval, these 2 scales are well separated. So there is a whole bunch of modes which fit into this quantum critical scaling behavior. So this is why we will associate the second regime to the quantum critical region. But the point is that as long as t approaches the upper bound, this interval starts to shrink. And at the same time, this interval expands. And eventually, we get a third regime for higher temperatures, which only has thermal NFL and Fermi liquid. So all the information about the quantum critical point has been erased here. So here we can see what I have just mentioned in this diagram, which plots temperature versus frequency. So again, red shaded regions are the ones which comprise the frequencies which scaling behavior is dominated by the quantum critical non-Fermi liquid. And the blue shaded region is the one for accounts for frequencies with dominated by thermal NFL, the square root T behavior. So the quantum critical point, of course, is the line at T equals 0, which only has quantum critical and Fermi liquid behavior. The quantum critical region, the second regime, is the one which displays the three possible scaling behaviors. And there is the third region, which only has the thermal NFL and the Fermi liquid. Of course, besides this scale, we have that all frequencies fit in the linear dispersion relations. But this is high temperatures. Okay. So is there any question before going to phenomenological consequences?
I have a question.
Sure.
Can you show again your expression for lambda t?
Lambda t, yeah. Here.
So my question is it it's smaller than t, right?
It's well, you have she.
Maybe it's
well, it's hard to say because you have a she to the 1/4 times t to the 3/4 times something which is a power of g squared over lambda, which is lower than 1, but you have to tune g in order, yeah.
But so your calculation is only controlled when g squared was much smaller than lambda, or
no, on the opposite regime.
The opposite,
so we are considering g squared much bigger than lambda.
Okay. I see. Okay. Yeah.
Yeah, that's kind of justified because g squared is a formal relevant coupling. So essentially, it will generically be large. And moreover, the lambda microscopically is related with g squared by inverse powers of m divide. So it is natural to assume that it is much lower than g squared.
Mm-hmm. Yeah, I was just wondering if lambda t is bigger than t. It seems like you have a very big, so your, you know, the kind of thermal regime in a typical theory, you don't expect it to hold for frequencies bigger than temperature.
Yeah, lambda t is actually bigger than well, yeah. It's hard to say because if you make the ratio between lambda t and t, you will have the two ratios, essentially a power of g squared over lambda to the 1/2, if you want. Mm-hmm. And you will have a ratio between g and t. And generically, t is much lower than g. G is one of the last scales appearing in these regimes, mm-hmm. not here. Mm-hmm. But on the other hand, the other ratio is pretty small. Mm-hmm. So, okay. Yeah. I don't have a concrete answer to that question. Yeah.
Thanks.
So let's try to discuss some phenomenological consequences of this. So the main point is that now we can gain a better intuition about the scaling behavior observed in a sample which contains such a critical point. And the first thing we have to do is to replace our naive intuition by the true one. And let's try to describe a bit this new phase diagram. So again, we have the inverse correlation length, or if you want, the characteristic energy of the fermionic excitations. We have these lines which go with the characteristic energy to the 3/2 again, and the critical region between these two lines. But now the crossover happens much before than expected. And above this new crossover, we will have a new scaling region, which is the thermal NFL, in which by how strong are were the IR divergences, in the finite model, there is a whole region in which the effects of having resolved them still dominates over the quantum effects. And this essentially the physical explanation for this new region. And the thing is that if this kind of model could be reproduced by an actual sample, one should find these two well-defined scaling behaviors. Namely, here you will have a 3/2, and here you will have, if you want, a 2/3, and here you will have a 1/2. That's essentially if you want, the prediction. So how much time do I have left?
10 minutes, 5 to 10 minutes.
Because I have some extra slides if you are interested in this superconductivity, but if now, I just assumed that here I'm jumping to the conclusion, but I have some more to say about superconductivity if you are interested. Just, it's up to you.
Maybe we can do conclusions, and then
Yeah,
whoever
sure,
wants to say.
sure.
Yeah.
Can I ask you a question?
Yeah, sure.
Sorry, before you move to the conclusion. So these exponents in the thermal non-Fermi liquid regime, how robust they are to the properties of the model that you assumed in the beginning, like the Z of the bosons, for example?
That's an excellent question. Actually, a priori, the existence of these divergences, and even in many cases the way we resolve it, is not actually very dependent on the actual dynamical exponent. It just depends on the existence of static modes without the mass. So my answer is that this will be pretty general for other models too. So in particular, why we are interested in Z = 3? Well, because it is a simple model you can actually solve and obtain all these properties, but it should be applicable to different dynamical exponents.
So is there a hope that this would like the exponents match the linear T resistivity or things like this that you see in the strange metal pairs?
Well, for computing the transport properties, there is still a lot to do from this point, because you need to analytically continue to real time and all that stuff. I'm not sure, because I haven't done the computation in one of the particular work we are interested in doing right now, but I'm not sure about the particular prediction for the resistivity, in the sense that it will of course be non-Fermi liquid, but I'm not sure about the actual exponent, and maybe there is more singular behavior that appears when you go to real time. There are a lot of subtleties usually there. There is an actual prediction you can do about the specific heat, because we haven't done it yet, but in particular that only amounts to compute the free energy on this normal phase. And there is actually a particular prediction you could do for the specific heat, but I don't have results so far. Okay, so let's go to the summary and conclusions. So we have characterized the quantum critical region associated with this critical point for a particular Z = 3 Gapless boson in interaction with the Fermi surface in a metallic system. Hopefully I convince you that this is interesting in both theoretical and phenomenological grounds. Theoretically, it stands as an example of a quantum field theory at finite temperature and finite density, which is free of IR divergences, which is not obviously the only one, but there are not, it doesn't happen so often as one would like. Most importantly, phenomenologically, it provides an important insight about plausible origin of anomalous behavior, which might be observed in strange metals. And finally, I haven't told you any about superconductivity, but in these models, it is very interesting to explore the stability underpairing of this kind of models to understand some aspects about high critical superconductivity. So pretty much related with one of the last questions, the mechanisms here, it doesn't seem to be actually dependent of the particular dynamical exponent. So it will be interesting to explore different dynamical exponents. For example, in Couperin-like samples, it is believed in some of the interpretations that the quantum critical point is associated more to an antiferromagnetic transition, which has said equal true because there is a magnetic ordering wave vector. It might be an interesting case to go further. There is also something which can happen. I have never talked about a possible gap function here or nothing, but it is true that if it were a solution to the Elias-Baer equations, including now a gap, and if it were a solution for the gap function, the back reaction of the gap in the boson will induce also a mass term for the static mode. And that will be also a possible resolution of the IR divergences. So an interesting question is whether both mechanisms are simultaneously possible, and if it is the case, which one will prefer most the system? That means which has less free energy. And this is by now a work in progress. So that's all. Thank you very much.
Okay, let's thank Jeremias for his interesting talk. Thank you with additional clap.
Thank you. Thank you.
Are there more questions? So I have a basic question. Maybe you mentioned it before, but my connection broke down.
Sure, please. Oh, I'm sorry to hear that.
Yeah.
Okay.
So is there a basic, simple way to see this dynamical scaling of the fermion at zero temperature, like the 3 halves?
You mean the critical point?
Yes.
Well, yeah, you can actually, yeah, these 2/3, you mean?
The 2/3, that's right.
Yeah, perfect. Yeah, yeah, generically, when you have a gapless boson interacting with the fermion, and this boson has a Z equals something dynamical exponent, you know what fermionic dynamical exponent to expect. It's pretty simple to write in terms of Z generically. In this case, it's 1/2. Okay. So it is perfectly, yeah. That's not new. That's nothing new.
About the finite, so in one of your final slides, you had this square root T dependence in the self energy. Is that also possible?
Here.
Yes. Is also here some simple argument one can find?
Well, no, actually here is, yeah, at least on my end, I don't have a simple argument. It's just what comes from resolving the Schwinger-Dyson equation in that particular regime.
Right. And do you expect it to be true at finite time?
Oh, you mean about, yeah, finite time corrections? Yeah, I'm not sure. I will expect to be pretty robust about, but yeah, actually, I think I don't have a good argument for that.
So could I, in principle, tackle this problem with an epsilon expansion type of approach?
Well, the epsilon expansion is the one which failed, actually.
Oh, okay. I guess I missed,
it is this. Yeah, exactly. This is what people call the epsilon expansion for solving this kind of issues.
Right.
And it actually worked perfectly in 3 minus epsilon dimensions, but it doesn't work in 2 plus epsilon.
And if I take epsilon to be, 1 or something, do I get,
Yeah, well, there is something pretty interesting there. If you look at the expansion in 3 minus epsilon for a similar model but in 1 higher dimension.
Yes.
There the divergences are less severe because you are in higher dimension, and you can solve it with this epsilon expansion.
Yes.
And if you look at the final result, which is now finite, and you continue the result to epsilon equal 1, which will be 3 minus 1, 2, you will have exactly the t to the 1/2 behavior.
Okay.
But if you try to do it from the two-dimensional point of view, you find that it is not the epsilon expansion which gives the t to the 1/2.
Yeah, because it's still relevant, I guess.
Because here it's relevant. Yeah.
Yeah.
Exactly.
Okay. Thanks.
I have a question related to the. Thanks for the nice talk, by the way, Jeremias. So related to the 1/n corrections. Do we expect generically to have fixed points where you have several values of z's for different fields in a theory without large n, where everything couples to everything?
Yes. Well, yeah.
Because here basically you have two scaling symmetries, right? In your fixed point, you have a scaling symmetry that acts on the boson and that has z equals 3, and a scaling symmetry that acts on the fermion. And I guess it's
but
kind of
no, but you have only one scaling symmetry, so the whole model is actually invariant under the, because yeah.
So what is z? Is z 3/2 or 3?
Well, I haven't been specific about that, but let me just say you that this scaling transformation of the momentum it's fake. It's just a simple expression for it. But what really happens is that the longitudinal component of the momentum transforms this way, but the perpendicular component, I'm just referring to the Fermi surface, transformed in a different way. So it happens what people call the factorization.
Okay, so the half just comes from the same thing that, like, the squared in the, I see.
Exactly.
Could you explain why Fermionic loop doesn't generate Sommer mass of this boson field, maybe in your first attempt to solve this problem?
Here. Okay, so this fermionic loop doesn't generate a mass for the static mode. So it generates a mass, if you want, for the high frequency modes. Note that if omega goes to infinity much quicker than the momentum, this essentially is a constant piece. But the modes we are interested in are actually the vanishing frequency modes. For those modes, this vanishes.
Okay, so just to compare what I know in the Sommer gauge theory, do you think this is same in this gauge theory with the finite fermion density?
Exactly, it's the same. Yeah.
Oh, I see. Okay, thank you.
Yeah, actually, what happens if you consider a gauge theory, actually you could say that our boson is also associated to the gauge. It might be associated to a gauge interaction a priori. So what happens when you consider, for example, a U1 boson, a gauge boson coupled to a finite density fermions, is that this, well, the expression is a bit more messy because you have various components, but essentially the longitudinal components become gap, but the transfer components, fluctuations of the gauge field, acquire this damping term. So it is, as you said, exactly what happens there too.
But for the time component gauge field, there is a Debye mass even in zero temperature with finite density, I think. So you are actually
the Debye mass is an effect there of finite density, not finite temperature. Exactly.
No, I'm saying is that for the this zero component of gauge field, there is a Debye mass at zero temperature.
Exactly. Yeah, it gets gapped. It's just an electrical screening, if you want, in the usual classical electromagnetic intuition. Yeah, yeah. But the transfer component, or what some people call the magnetic component, doesn't get a Debye mass. it acquired the Landau damping.
Thanks.
Can I ask a question about your starting point? And you start with gapless boson with device screening. Some overdamped term.
Overdamped, Landau damping.
But if you start with the theory with without that overdamped term, but with gapless boson and the gapless fermion, and also the Yukawa interaction term without this overdamped term, you cannot obtain the your quantum critical point. Or what is the difference with that model?
Yeah, it's a great question. Actually, if you consider this relativistic boson at the starting point, then the first fermionic correction will lead. So no matter how small the prefactor might be, there will be frequencies low enough such that for low enough energies, this term will lead the dynamics of the boson. So you will eventually obtain the Landau, the overdamped boson anyway. Yeah.
And then you expect that the universality class is the same.
Exactly. Yeah. But that kind of model, if we were considering that the Landau damping is generated by the same fermions we are considering in our model, it has some subtleties which are solvable, but it is more tricky. That's why I haven't discussed it here. But it's exactly what you say. You will expect to fall in the same universality class.
Thank you.
More questions? If not, let's thank Jeremias again. You can maybe, people can leave. You can something about the superconductivity.
Sure. If you want, I can add something about that. Let me go to it. So, what about superconductivity? Just let me be very brief here. What I'm telling you about here is about some conclusions that can be extracted by studying the critical point. So the following is not a finite T analysis. Of course, a finite T resolution of the full Eliashberg system is required for quantitative, for having quantitative precise results. But it turns out that only considering the zero temperature model leads to qualitatively very accurate results, and even though quantitatively in some cases. So let me just discuss the characteristics of the critical point under pairing. So in a nutshell, the main result is that there will be a critical value for the rank of the flavor group, this n. And above this critical value, so for very, very large n's, the model will flow to a quantum critical point with finite BCS. So there is no pairing instability there. And the converse happens for n small enough. So physically, this is the reason. The main reason is that the presence of the gapless boson, it's dual, if you want, has a dual consequence. On one side, the one effect that we have discussed most in this chart, in this talk, is that it destroys quasi-particles. So it leads to incoherent states, which it's equivalent to say that the model acquires NFL dynamics. But on the other hand, it has a singular contribution to the BCS vertex by means of, for example, if you want perturbativity, this will be the diagram, which tends to enhance the pairing attraction. So, well, this kind of contribution might be in any channel in principle, but by the symmetries of our model, it happens in the S channel, but there are other models in which it happens in the D channel, for example. And the main point here is that these two effects compete with each other. And why is that? Well, essentially because if you destroy the coherence of the quasi-particles, they get a mean lifetime which is shortened, and so they have less chances to participate on the formation of a Cooper pair. So this is physically the picture, and if you want mathematically, the result is a critical value for the rank group. And one can see it pretty easily by various methods, which turn out to be all equivalent. Here I show you the perturbative method, if you want, which is an inertia treatment of this. These three diagrams essentially gives you this beta function for the BCS coupling. And here we see this is the dressing of the quasi-particles, so it has to do with the NFL behavior. And on the other hand, this is the boson exchange here. And this is the universal minus lambda square, which is generated at one loop in the BCS channel. So the effect of these new two terms is that the beta function has two zeros, which are real only for n bigger than 8. While for n lower than 8, these become complex, and the model has no other choice than go into a divergent lambda at a finite mu scale. And this is essentially pictured in this cartoon. So for n less than 8, you will find a critical region with NFL dynamics, but you won't be able to reach the quantum critical point at 0 temperature because there is superconductivity arising at some finite t. On the other hand, if you were able to tailor a sample with these characteristics, with this n and this n bigger than 8, you will find the critical region, but you will be able to reach t equals 0 and find a quantum critical point with finite BCS coupling. The last feature about this phenomenon is that, as you can see, the fixed points coincide or collide, if you want, at n approaching 8. And also, if you compute the correlation lengths for n near 8, you will have these divergencies, this non-analytic divergency. And these are usually signals of a BKT transition. So one can characterize the transition here as a BKT. Okay, but again, a full treatment of the Liashberg equations of finite t, let me just spoil the result that will confirm many of the facts I just told you here from the t equals 0 picture. But that's a work in progress right now. Yeah.
And zero temperature story, where is it? Like in which work?
Oh, the zero temperature story. No, actually, well, we actually knew about this when we released the zero temperature paper with Shri and Shamit, but we haven't included there. I assume that in our well, there is an appendix in the new paper released about finite t, which tells about the zero temperature story that I just mentioned you. Not very detailed, but in the next publication about the actual solution of finite t, we will be more concrete, probably.
Okay.
But just to mention that this is not new. It's not that we are the only ones who find this. This is pretty old. There are a lot of models which find a similar effect. So just to be clear about that.
Are there other questions?
Can I ask a very naive question about the quantum critical point? And so
sure.
You start with okay. If you have the quantum critical point, maybe it separates the two phases. I guess you have the some phase at the for example, in the case of the Ising case, we have the paramagnetic phase and the ordered phase.
Yeah.
And in this case, what is such kind of, how to say, the corresponding phase for the
well, perfect. Nice question. Generically, this Z equals 3 boson is associated to a ferromagnetic Ising transition. And it's also associated to the Ising nematic transition. But in the case of the nematic transition, if there is a Pomerantz-Schuck instability, you will have that the coupling of the boson is not spherically symmetric. You know, you have cold spots there. That's a bit more tricky.
So we can think of this gapless boson as a nematic Nambu-Gaussian mode.
Well, yeah, but I have to say that I'm not an expert on that, but I guess that there is a non-trivial angular behavior on the coupling of the boson with the fermion. So if you want this effective coupling depends on the angle. There are angles in which this coupling is maximum, and there are angles in which this coupling is zero. So it's not exactly what we are considering here. But that's a pretty interesting case from the point of view of superconductivity, because it naturally induces a D-wave pairing, which is more common in cuprate-like experiments.
Thank you.
Welcome.
More questions? Okay. Well, let's thank Jeremias again.
Thank you very much.
Jeremias.
Thank you.
Good. Okay. Enjoy the rest of your day, everybody.
Okay, thank you very much for the invitation. It was nice.
Bye-bye.
See you.